Hi, this lecture is about section 12.3, which is the dot product and vector projections. So 12.3, dot product and vector projections. Actually, two different topics here for the title. And there's more than two topics in the whole section, but that's the title of the section. Okay? So let's start with the dot product. It's actually not that complicated. It's pretty easy to calculate. And before we talk about the dot product, let's mention the other kind of multiplication we've dealt with in this course. So we learned about scalar multiplication. Scalar multiplication in the previous section. And a scalar multiplication is a scalar, which is going to be a real number, scalar times a vector. So we learned that in the previous section, 12.2. Okay? So that's what we learned in 12.2. That's scalar multiplication. So for example, if you have 2 times vector v, that's considered scalar multiplication because 2 is a scalar. It's a real number. It's not actually a vector. Okay? We learned that in the previous section. Now in this section, we're going to be learning about what's called the dot product, where instead of multiplying a scalar times a vector, we're actually going to multiply a vector times a vector. Okay, so the dot product is what we're learning in this section. And that's going to be a vector times a vector. A vector times a vector. Okay, so for example, we could have vector u times vector v. Vector u times vector v. And the thing is, we put a little dot there. That dot is important. That's what makes it a dot product. And in the next section, we'll be learning about the cross product, which is another type of vector multiplication. But the basic idea with the dot product is it's a way of combining a vector with another vector that's sort of like vector multiplication. Okay, so let's see an example of the dot product. It's actually very straightforward to calculate, and it's very useful in physics. Okay, so example. Find the dot product. Find the dot product u dot b. Okay, so people like to say u dot b or the dot product of u and b. Okay, and for this problem, they're telling us that vector u is equal to 6i plus 3j minus 2k. Okay, so 6i plus 3j minus 2k. And so that's our u, and then our v, so vector v is equal to 12i plus 35j. 12i plus 35j. Okay, and we want to find the dot product u dot v. So how are we going to do that? Well, to find a dot product, you basically just multiply the components of the vectors. Okay? So the basic idea here is write in component form, so write as a position vector. So you write in component form, then multiply the components. And then you add them to each other. And add them to each other. So that's kind of awkward to say in a sentence, but it's actually very simple once you realize how it works to actually write it out. So to write it in component form, our vector u is going to be 6i plus 3j minus 2k. So that's going to be 6, comma 3, comma negative 2. Okay? And then for vector v, writing that one in component form, we have 12i plus 35j. So that's going to be 12, comma 35, but then we need to have a last component. Now if you look up here at vector v, it has an I, which is the x component. It has a j, which is the y component, but it's missing a k, which is the z component. So for that one that it's missing, we're going to have to put in a 0. If you wanted to, you could even write a plus 0k over here. Some people like to do that to remind themselves that it's still there. But for this component form, because u is a three-dimensional vector, v also has to be a three-dimensional vector. So if they don't write a component like that, it's 0. So v should actually be 12, comma 35, comma 0. So I'm going to go ahead and write that in. And if you're ever missing an I or a J or a K, just remember that it's automatically a 0 if they don't write anything for it. So that component's going to be a 0. Okay, so now I said when you're taking the dot product, first you write it in component form. We did that. And then you multiply the components and add them to each other. Okay, so what's that going to look like? Well, u dot v means we multiply the components. So let me do it with colors here. So we got the first components, we got 6 times 12. 6 times 12. So that's going to be the first multiplication that we do here. And then the second component is 3 times 35. So we're going to be doing plus 3 times 35. Okay? And then for the last component, we're multiplying those, so that's going to be negative 2 times 0. So we do plus negative 2 times 0. Okay, so that's what I mean when I say you multiply each component individually, and then you add all of those components to each other. So here we're going to have 6 times 12, which is 72. And then 3 times 35, well, 3 times 5 is 15, 3 times 30 is 90, so that's going to be 105. So we have 72 plus 105. And then negative 2 times 0 is just 0. And remember, you can use a calculator if you ever want to. This one's not that bad, so I'm not bothering to use a calculator. Okay, so what we got here is 72 plus 105, since this last component is 0. So that's going to be 177. 177. Okay? And I'm going to box this. This is actually u dot v. Okay? So that is the idea with finding a dot product. And you can also do these for two-dimensional vectors. It's just with a two-dimensional vector, you only have 2 components, but you still multiply the first components and add them to the product of the second components. But it's the same idea. Okay? Alright. Okay, cool. So I wanted to give you some general formulas involving this new dot product. So let's learn some formulas for the dot product. Now the first one you can probably already guess how it's going to look based on what we did up there. So if you have two vectors u and b, so if you have vector u equals the component form u1, u2, comma u3, and vector v is equal to v1, comma v2, comma v3, we have the following formulas. We have the following formulas. Okay, so the one that people use the most is one that describes what we were just doing above. So that would be u dot v is just going to be, you multiply each component and you add them all up. So that would be u1 v1 plus u2 v2 plus u3 v3. Okay, so that would be the one that we just used above, which is actually really simple. You multiply each component and you add them all up. Okay, so that's the first formula. Call that formula number 1. And there's some other helpful formulas for the dot product, but they aren't used as often. However, they do show up in your homework. So we're going to do another one here. So formula number 2 actually involves cosine. So hopefully you remember some of your trig and your pre-calculus. You're going to use that here. So the next formula is cosine of theta. We'll talk about what theta is in just a second. Cosine of theta equals u dot v. Okay, so u dot v all over the length of u times the length of v. Okay? And theta is actually just the angle between the two vectors. Okay? So theta is the angle. Theta is the angle between u and v. Okay? So that's important. Let me write that. Let me underline that. So theta is the angle between u and v. Now, how do you find that angle? Well, in most problems, they won't be asking you to just find the angle randomly. You'll be able to figure out what the dot product is, and then you can use this formula to actually find theta. Or sometimes they'll just ask you to find cosine of theta. Okay? So those are probably the two most important formulas for dot product, and we may learn some other ones later, for example, vector projections. But that should be enough formulas for now, and we'll write more later. But I wanted to go into another example, and this time we're going to try to use this second formula here. The cosine of theta equals u dot v all over the length of u times the length of v, this whole thing. Okay, so new example. Find the cosine of the angle between v and u. Find the cosine of the angle between v and u. Okay? And for this one, we're going to write down some new vectors here. So we're going to do vector V. Vector V is going to equal 6i hat plus 2j hat minus 3k hat. And again, those hats are going to be actually just bold on your homework. And then the other vector is going to be u. So here our u is 8i, so 8i hat plus 15j hat. So in this problem, they actually want us to find the cosine of the angle between v and u. So we're going to be able to use this new formula because notice the left side of this formula is cosine of theta, where theta is the angle between u and v. And keep in mind that the order of your dot product doesn't really matter. So u dot v is actually going to be the same as v dot u, because when you're multiplying and when you're adding, the order doesn't matter. So if we want to find the cosine of the angle between v and u, we're going to use our new formula. So we're going to find cosine of theta equals u dot v over the length of u times the length of v. So that new formula. And notice they're not actually asking us to find the angle. They're asking us to find cosine of the angle. So whatever we solve for here, that's going to be our answer. So I'm going to go ahead and try to do this all at once. Some people would write it out in more steps, but I like to do it all at once. So let's do u dot v first. So u dot v is going to be the first components multiplied together, so that's going to be 6 times 8, plus the second components multiplied together, so that's going to be 2 times 15. So 6 times 8 plus 2 times 15. And then we're going to have plus the third components multiplied together. Well, what's the third component here? Well, since they didn't write a k, just like the last problem, this is going to be 0k. Okay, so the third components are going to be negative 3 times 0. So plus negative 3 times 0. All right, and then this is all over the length of u times the length of v. So that's going to be the square root of 8 squared plus 15 squared. That's for u. And then for the length of v, we're going to have the square root of the sum of the squares. So that's going to be the square root of 6 squared plus 2 squared plus negative 3 quantity squared. Okay, so 6 squared plus 2 squared plus the quantity negative 3 quantity squared. Okay, and then we can just simplify all this. So top left we have 6 times 8 is 48. Top middle 2 times 15 is 30. So we have 48 plus 30. And then negative 3 times 0 is just 0. Okay, so on the top we have 48 plus 30. And then 8 squared is 64 on bottom left. So we have 64 plus 15 squared is 225. So 64 plus 225, if you want to, you can use your calculator if you're feeling lazy. I'm going to go ahead and use it, even though I could probably add that. So 64 plus 225 gives me 289. So on the bottom left, I have the square root of 289. And then on the bottom right, I The square root, well, 6 squared is 36. 2 squared is 4. And then negative 3 quantity squared, the minuses cancel, and that gives us a positive 9. Okay, so we have 36 plus 4 is 40, plus 9 is 49. So on the bottom right we have 49. And then we can simplify this a bit more. On the top, we have 48 plus 30, which is going to be 78. And then on the bottom, we have the square root of 289. Now the square root of 289, if you can't do that in your head, you can go back to your calculator, type in 289, and then press the square root button, and it turns out that it's actually 17. Okay. So on the bottom we're going to have 17, and then the square root of 49, as most of you know, is 7. So on the bottom we'll have 17 times 7. Okay? And then I don't believe there are any common factors there, but you can always check on your calculator. You can try 78 divided by 7. That does not work. And then 78 divided by 17 also does not work. It just gives you a decimal. So that means there are no common factors there. So we can go ahead and just do 17 times 7, which gives us 119 on the bottom. Okay, so on the bottom there, we've got 119. Okay, so we have 78 over 119. Now you might be kind of confused. You might think, well, didn't they ask us to find cosine of the angle? Shouldn't that be in degrees or radians? Well, if you're wondering that, it's understandable that you'd be wondering that, but remember, they didn't ask us to find the angle. They asked us to find cosine of the angle. So this answer here is actually going to be cosine of the angle, which is what they asked for. So here you don't have to worry about degrees or radians, because this is actually a value of a cosine. Remember, cosine is adjacent over hypotenuse. So here we're saying the adjacent is 78 and the hypotenuse is 119. So that's actually correct. And you don't need to write degrees or radians here. Okay, so that's our answer. Alright, so that's the cosine of the angle between two vectors. And now I wanted to write some more formulas involving the dot product. So, more formulas. Some of these are hard for me to describe in words. If you want to see a nice picture, you can look in our book. Remember, you have access to the e-text over my math lab. But I'll give you my best in words. So first of all, a formula I wanted to show you is, it's called the scalar component of u in the direction of v. Scalar component of u in the direction of v. In the direction of v. And that's actually the whole name of it. It's a pretty long name. And the idea with it is, roughly speaking, if you think of two vectors, if you look at the scalar component of one of the vectors in the direction of the other one, you can sort of think of it as how much this first vector is pointing along the other vector, roughly speaking. And you're describing it as a scalar, so you're sort of measuring how much of one vector goes in the direction of the other one, and you're measuring it as a scalar, which is just going to be a real number. And if you want some nice pictures, they're too complicated for me to draw on here, but there are some nice pictures in our e-text in our book. But anyway, the formula for this is going to be u dot v all over the length of v. u dot v, u dot v, all over the length of v. Okay? That's the scalar component of u and the direction of v. Okay? And then I wanted to talk about one more formula. This is the biggest formula we've seen involving the dot product. And this one is called the vector projection of u onto v. So this is, that last one was a formula number 3. And now we're going to have formula number 4, which is the vector projection of u onto v. The vector projection of u onto v. Okay, and this one's even harder to say in words. But again, going back to the idea, if you have two vectors pointing in different directions, the vector projection is going to take the first vector and sort of project it onto the other vector. Sort of like if you go to a movie theater, you have a big screen and an image is projected onto the big screen from the projector. Well, with two vectors, the first vector is going to be projected onto the other vector almost as if the other vector were like a movie screen, if you will, even though it's only one-dimensional. That's the basic idea. And however much of the first vector goes onto the other vector, for a vector projection, that's going to form a new vector here. And that new vector is called the vector projection of u onto v. And again, our book has some nice pictures of that, but here we're mostly here to learn about the math, not so much the details of the pictures. Okay, so the vector projection of u onto v, our formula is written, rather complicated formula, I'm not going to lie. It's not that hard to use, it just looks complicated. So the way it's written is you write PROJ, that stands for projection, and then we write a little v as a subscript, and then we write a big U as an actual letter there. So that's the vector projection of u onto v. Okay, and this is equal to a big formula. So here we have big parentheses, and then we have a fraction. In the numerator of the fraction, we have u dot v, u dot v. And then in the denominator, we actually have the length of v squared. So we're squaring the length of v in the denominator. And then we end these parentheses, and believe it or not, there's even more here. Now, after all that, we have a v, just the vector itself, out front. Okay, so the vector projection of u onto v, written proj v u, projection of u onto v, equals parentheses u dot v all over the length of v squared, parentheses times v. That's quite a big formula. But hopefully at this point you're comfortable with the dot product and also the length and just vectors in general. Okay, so, oops, hate it when I do that. Let me fix that. Okay, so let's do one more example where we get to use these two formulas. All right. Example. Given the vectors, oh, that got messy. Sorry, having pen problems here. Given the vectors, v equals 15i minus 6k, v equals 15i minus 6k, and u, vector u, is equal to I plus j plus k, I plus j plus k. They want us to find these two new things that they asked for. So first of all, we want to find the scalar component of u in the direction of v. Okay, so that's going to be part number 1 here, is find the scalar component of u, find the scalar component of u in the direction of v. In the direction of v. Okay, that will be part 1 of our example. And I just wrote the formula up here. So we said the formula is u dot v all over the length of v. Okay, so u dot v all over the length of v. So I'll write that down. U dot v all over the length of v. And you could separately figure out the length of v and u dot v, but I like to just do it all at once, personally. So in the numerator, I'll do u dot v. Now, notice for v, we're actually missing a term. And you got to be careful here. We have an I and we have a k, but we don't have a j. So for v, we actually have 0 as the middle component. Okay, so that's important. Don't miss little details like that. Okay, so u dot v is going to be, I'll go ahead and write them out. So u is going to be 1, 1, 1, written as a position vector. Why is it 1, 1, 1? Well, because we have an I, a positive j, and a positive k. If they don't write the coefficient, it's automatically a 1. So it's 1, 1, dot v. Well, v is going to be, the first component is 15, but like I said, we're missing a j here. So since we're missing a j here, the second component is going to be 0. Because remember, j corresponds to the y component. Okay, and then for the last component, we've got negative 6, because we have negative 6k up there. Okay, so we should have 1, 1, dotted with 15, 0, negative 6. And then this is all over vector v, but we're taking the magnitude of v, or the length of v. So that's going to be the square root of 15 squared plus negative 6 squared. Okay? And you could do these separately, but I personally just like to do it like this, where I do it all at once. So in the numerator, when we're multiplying, for the dot product, we multiply the components. So it's going to give us 1 times 15 plus 1 times 0 plus 1 times negative 6. All over the square root of, well, 15 squared is 225. If you don't remember that, you can use a calculator. And then negative 6 quantity squared is going to give us positive 36. So under the square root on the bottom, you should have 225 plus 36. And so on the top, we've got 15 plus 0 minus 6. So we get 15 minus 6 is 9 on the top. And then on the bottom, 225 plus 36 is going to be 261. but we still have a square root around that. And if you're not sure if you can take the square root of 261, you can always hop on your calculator. So we do 261, the square root button. And as we can see, then that one is actually not something you can take the square root of. So you could try factoring it. If you have a more complicated calculator, it might simplify square roots for you. In fact, the TI-30XS is what I recommend for that. But this one I don't believe can be simplified a whole lot. You can try dividing 261 by different numbers, like 3, well, it's 3 times 87. Okay, and then 87 divided by 3 is 29. So it's actually going to be 9 times 29. Yeah, so we can factor it. But again, if you want to use a calculator for that, I recommend the TI-30XS. That scientific calculator is really nice, and it allows you to actually just type it in, and then it'll simplify the square root. Okay, but what we have here is actually, in the denominator, we have the square root of 9 times the square root of 29. Okay? The square root of 9 times the square root of 29. Because 9 times 29, we said, was 261. Okay? And then simplifying that, we know that the square root of 9 is 3. So on the top we have 9, on the bottom we have 3 root 29. And with root 29 you can't simplify it because it's actually, I believe, a prime number. Alright, but we can do 9 divided by 3, and that's going to give us a 3 on the top. So we get 3 over root 29 as our answer. Okay, and in other classes you might be used to rationalizing, but in our book, for whatever reason, they don't bother to rationalize it. So this is actually going to be our answer. So you don't actually have to get rid of the square root in the denominator here. This is acceptable. Okay, so we got to use one of the new formulas. We learned how to use scalar component of u in the direction of v. That one's not so bad. Now we're going to take a look at formula number 4, the vector projection of u onto v. That one's a bit more complicated, but as you'll notice, it's still just a dot product, and then a length down here squared, and then at the end you multiply it times a vector. So even though it looks complicated, it's not as bad as it looks. Okay, so let's do that. Okay, so part 2 of our example. They want us to find the projection of u onto v. Find the projection of u, vector u, onto vector v. So in other words, they want us to find, how do we write it? We write it as PROJ for projection, and then we write a little subscript of v, and then we write a u as an actual letter. Okay. And writing down the formula, and go back up here and get it again. The formula is going to be right here, which is the quantity u dot v over the length of v squared, all times v. So writing it down, we've got the quantity u dot v, quantity u dot v, over the length of v squared, parentheses around all of that, and then we have v. Okay? And for this problem, we said that vector u was I plus j plus k, and vector v was 15I minus 6k. Well, we already did u dot v. So notice we did u dot v up here, and we said that it was 15 plus 0 minus 6, which was 9. So u dot v is already done, and we said that that was 9. So we can write that in here. So our numerator is going to be 9. And then for our denominator, we have the length of v squared. But remember, we already did the length of v in part 1 of this example. So the length of v was actually the square root of 15 squared plus the quantity negative 6 quantity squared, which ended up being the square root of 225 plus 36, which is the square root of 261, and that simplified to 3 root 29. So we can actually just plug in 3 root 29 if you want, or even easier maybe is to plug in the square root of 261 and then just go ahead and square it. Either way is fine. I'm going to just plug in the square root of 261 because I know that I'm going to square it anyway, so there's no need to simplify the square root. So we're going to have the square root of 261 squared, and then we have all this times vector v. So what was vector v in component form? Well, we said that it was 15, 0, negative 6. 15, 0, negative 6. And I like to write it in the component form or as a position vector. I just find it's easier to work with than the ijk, but some people prefer to write it as ijk the whole time. It's really up to you. But as you can see here, first we have to simplify what's on the left. So the square root and the square cancel out, so we just get 261. And then recall that 261 is actually 9 times 29. So on the top we have 9, on the bottom we have 9 times 29. So the 9's cancel out, and we just get 1 over 29 times the vector 15, 0, negative 6. Okay? And that's actually going to give us 1 over 29 times 15, 0, negative 6. And then for your homework, they want you to go ahead and distribute. Okay, so they want you to distribute the 1 over 29 to each individual component, just like we always do with scalar multiplication. Okay, so that's going to give us, for the first component, we're going to have 15 over 29. For the second component, we're going to have 0. And then for the third component, we're going to have negative 6 over 29. And remember, 29, I believe, is a prime number. It certainly doesn't show up in your times table, so there's no common factors here. And then also in your homework, at the very end, they want you to write your answer in terms of unit vectors. So we're going to go ahead and write it as 15 over 29 times I. We don't write the middle term because it's 0. So if the j term is 0, you don't write it. And then we write the last term, which is negative 6 over 29 times k. Okay, so our answer is 15 over 29 times I minus 6 over 29 times k. And that completes our lesson on the dot product and vector projection.